Today we're looking at 8.2 combined with 6.3 and 6.4. So we're focusing on stretching and compressing functions. And in the warm-up, we do a little review of yesterday. So we're going to take the function cos x and we're going to shift it up 2, which just means that we add 2 at the end of the function. Or we're going to shift it left pi over 4, which means we're going to put an x plus pi over 4 all in the parentheses. So how you type this into a calculator is really quite different because of the parentheses usage. Go ahead and choose the option for C. And since we are moving the function left 2 pi over 3, we want a plus 2 pi over 3 on the inside. And since we're shifting it down 3, we want a minus 3 on the outside. Go ahead and choose the option for D as well. Now let's move on to applying some of these stretches and compressions into context. So in example 1, we're going to do a little cooking here. We got a yam, we put in the oven. The oven's 150 degrees. And the table here on the left shows all the temperatures of the yam for different time values. So we're going to plot these points and sketch a graph. Go ahead and pause this video to make your graph. So I have scaled my axes. I'm just going to label them as T for time and capital H for temperature. And I'm going to plot all these points as best I can to get the relative curve of this function. Notice it is not going to be a linear function. It's going to flatten out as it goes to the right. So that's going to be important to what we talk about today. And I'm just completing the rest of this and it gets to about here. So my function looks something-ish like this perhaps. And that's my R of t function. We're going to get another graph on here in a minute. So I want to make sure to label that. So the first thing we want to do is describe the function in words. What is happening to the temperature? Go ahead and choose the option in the Edpuzzle that makes the most sense. And hopefully you choose some type of an option that says that the function is increasing, but it is slowing down as the time values increase, or maybe even something about it approaching 150 degrees. Now we're going to take part C, and in part C, they ask us to make a new table. We are going to make this table by multiplying all of our R of t outputs by 1.5. Go ahead and generate that table and make the graph for part C. So your table that you have here is all of the same output values you had before multiplied by 1.5. And when you graph this function on the same graph, you should have basically the same shape. But when you go ahead and create these new values, you just see that it gets a little bit stretched up here. So these are just hitting a little bit higher than we had the first time. So it looks something like this. And I'm not hitting all those perfectly, but that's the idea. So this second function is what we say vertically stretched. It's getting stretched out. It's not shifted because you'll notice the 0, 0 point didn't move at all, and they're not moving up an even amount, but I am stretching out those values. Go ahead and choose the option for part D that best describes how Q and R are related. And there might be multiple options that all work here. So choose all that apply on part D. Now, the very last part of this problem is part E, which is on the next page. What they want you to do on this problem is for each of the two yams, so the Q of t and the R of t functions, find the rate of change of temperature. So we have to go back to remembering what rate of change is. We haven't talked about this since last try. And remember, rate of change is essentially the idea of slope. So what we're going to do is we're going to set time intervals from 0 to 10. We're going to continue this. 10 to 20, etc. You're going to go all the way up to the 50 to 60 time intervals. So we're going to break this up into 10-minute intervals for the first 60 minutes. And then we're going to calculate the rate of change values. So you're going to do R of 0 minus R of 10 using your table over 0 minus 10. And you're going to do all of these. Go ahead and pause this video to complete that table. And one little relationship that you might notice, and you might not have noticed, and that's totally fine, is that the average rate of change of R and the average rate of change of Q are similar, and they have a 1.5 multiplied ratio as well. And that's what this next box says. So it says, if we take a constant K and we throw it in front of a function, so Y is K times f of x, then our function is vertically stretched by that value K when K is bigger than 1. It's compressed by by k if k is less than 1, but specifically we say between 0 and 1, because if it's negative, then what it does is it reflects it over the x-axis. So we reflect over the x-axis when k is a negative value. Now, the last part here talks about that average rate of change problem. And this just says that if we have a vertical stretch or compression, then the average rate of change has that same ratio as well. So that can be a useful concept moving forward. Now, moving on to example 2, we are given the function again, y equals x squared. So we're going to go ahead and graph that 1, 1, 2, 4. I like to reflect those over. And this is just my parent function for quadratics, right? And we're going to go ahead and make this new function. And I don't have an equation. I only have it in terms of transformations. So what we're going to do is list our transformations. And the hint that's given to you there is that you work your way out. So we're going to start with the innermost transformation. The thing closest to the x is the plus 3. And we know that that will move our graph left 3. So you're going to shift everybody to the left 3. I'm going to go ahead and move those points over as well. And I'm going to kind of draw it just as a dash because this is just one of my kind of intermediate steps here. Then we're going to move to the next outer thing that we see. I see in front a negative 1/2. That's going to do two things. That's going to reflect it over the x-axis and also vertically compress it by 1/2. So we are going to do both of those things in one step. The order actually does not matter for both of those. So we're going to do both of those. So we're going to vertically compress and reflect it. So this point on the x-axis doesn't move. The point at negative 3, 1 flips over to negative 1 and then also gets shrunken down. So the output is only at negative 1/2. Same thing with these guys as well. So we are flipping it over and also compressing those y values or multiplying them by 1/2 there. The very last thing we will do is the most outer transformation, which is this -1 at the end. That will shift our function down 1. So you'll take all your points you have now, shift them all down 1, and that'll give you your final graph here. And that should look like your new function. So we have to rely on transformations when we don't actually have the equation to be able to figure that out. Now, example 3 can get pretty tricky. What I'd like you to do first is pause this video to make your graph based on those points. So plot those points and connect them. And once I have the points plotted, I'm going to go ahead and connect them. And I'm going to assume it's a smooth curve. Of course, I don't really know what that looks like, so I'm just doing my best, but I'm not assuming they're linear. So just going through. And I want to now make a table and a graph of this next function. Personally, I like to do the table first. Some of you visual people are going to want to do the graph first. Either way is fine with me. Let's identify this transformation. Since it is an inside change, it is going to do the opposite of what you think. So it looks like it's going to half my x values. Instead, it is going to double my x values or horizontally compress my function. So I'm going to take all of my x values and instead of halving them, I do the opposite and I will double them. So they become -6, -4, etc. Go ahead and complete this table. Your y values do not get affected. So it's still a 0 and then a 2, etc. So I'm going to plot all of these new points and hopefully it'll look like a horizontal compression. Sorry, I'm saying horizontal compression. I mean to say horizontal stretch. My apologies. Because again, the 1/2 is the opposite. So we're really timesing it by 2, which means we're stretching it out. So we're going to go ahead and stretch this out. So we go over to -6, 0. We go to -4, 2, etc. When you plot all these points and you go through and you connect them, you should see that this thing looks like a stretched out version of what we had in the first graph. So that's how we horizontally stretch the function. Again, horizontal stretches and compresses are always way more difficult than the vertical ones because of that kind of opposite thinking we have to do. So on the top of the next page, you will see your notes box here. When you have a K on the inside, you compress by 1 over k if k is bigger than 1. So if your number is like 1/2, then you're compressing it by 2, essentially, which means 1/2. Sorry, I just said that's super confusing. Here's what I meant to say. If your k is 2, so if k is bigger than 1, so let's say k is 2, then this thing looks like f of 2x or whatever, right? So it appears that you're multiplying by 2. What you're really going to do is you're going to horizontally compress by 1/2. That's what this is trying to say. Vice versa, we are going to horizontally stretch by 1 over k when k is between 0 and 1. If your k is negative, then of course we will have a reflection, and this time it'll be reflected over the y-axis. Let's try one more of these. What I'd like you to do on example 4 is I would like you to try to match which function is which graph. So knowing that these are all inside stretches or compressions because they are in with the input, keep in mind how that affects it. We know that the 2t is going to actually do a compression by 1/2, whereas the 0.5t and the 0.8t will both do a horizontal stretch. So those are going to be the two more outer functions. And then the first two functions will either be the compressed or the original. Since this one is compressed, we want that guy to go in first. So my graph A is j of t. And then f of t will be this graph B. After that, I have two that are getting stretched. See if you can identify which one is which. So first tell me which graph is C and then which one is D. And we should have found that graph C is the h of t function. That's going to be the 0.81. And then the graph D is the g of t function, and that's going to be the 0.5. And if you got confused by that, I'd like you to put a note here. The smallest k will actually have the biggest stretch. The smallest k will actually have the biggest stretch. So the smaller the k, the more it's getting stretched out.